Okay, so then we say welcome to the class. And for today, I would talk about Aerosol Transport II, and I would like to ask if one of you could repeat what we did last week and the last 2 weeks. So what was the class content of last week, and it was connected to the last 2 weeks? Yeah? So we talked about Brownian motions. What is Brownian motions? Very good. You already mentioned it a little bit, but maybe somebody else can repeat it. What is Brownian motions for aerosol particles? Was it the collision of the particles with each other? And how is it caused? It's a movement, that's right. So basically, where is the Brownian motion? How do we describe the movement of particles, of aerosol particles? Yeah? Yeah, it's randomly, that's very good. It has no direction. But what is Brownian motion? Yeah? Sorry, I'm still a little bit ill. Exactly, but so what happens? So you said the higher the temperature, the more they move. You said it's a random movement. You talked about the one-dimensional Dirac pulse, basically. Why we had this? Why we had this one-dimensional model? Yeah? Yeah, what's simpler? What do we want to make simpler? Which equation? Navier-Stokes, exactly. And in the Navier-Stokes, we have one term which is related to Brownian motion, and this is diffusion, right? So is Brownian motion diffusion? Yeah? Yes. And what is different to the diffusion of molecules? Or is it the same? What was the difference of Brownian motions to the diffusion of molecules? Yes, Brownian motion is the driving force of diffusion, but your neighbor already basically told it in the correct way, but there was some very important information missing. What happens to the particle? What causes the Brownian motion of the small particle? Yeah?
Like you asked for difference, like there is no, like for Brown's motion, there is no specific direction for traveling.
Yeah.
For diffusion, it has a particle go from higher concentration to lower concentration.
Yeah, but this also counts for one. If you have a lot of particles and you have a concentration gradient, they will also go to the concentration. But how does a single particle moves by Brownian motions? Very important. What happens to this particle? Yeah?
I can remember that you showed us a video.
Yeah. So what do the molecules with the particles? Correct what you're saying? They're hitting it, right? So and if these guys hitting the particle, what happens with the particle? It moves, right? What happens if these molecules hit me? Nothing, right? I don't move. So Brownian motion is important for small particles. But the molecules move because of their kinetic energy. This causes random movement. And the nanoparticles, they don't have enough kinetic energy to move by themselves, but they are in a size range where they see and feel the molecules which are moving. And if they hit the particle moves. And this is what we saw in the video, right? With these larger and the smaller ones, okay? So remember the video, please. Good. So for today, we will be here, right? And I will try to, till tomorrow, prepare a homework for you, your first homework. Okay, so what happens, who can explain what happens with this homework? So now it's your first homework. How do, you know how it works with the homeworks, right? Mm-hmm. Yeah, I have no way to make a fair decision. Next day, said, I trust one day. Ilias is fair. If you cannot upload on Ilias, it's not my problem. If Ilias has technical problems, which normally does not happen, it's not my problem if you ask me this 5 minutes before the deadline. If you ask me this 1 day before, I can try to help you, okay? Yeah. Yeah. So the thing is, probably I will give you also an extra day because 1st May is free day here. So I will probably, if I upload tomorrow, I will give you till Wednesday next week, so 1 extra day. But I will put the deadline in the homework. So please read the document till the end. There will be very red marked letters with the rules when to upload. And there's also something, you can do this in groups, but every person has to upload his own document. I would do it in a group if I were you. It works much, much better. And I will also give, so normally you get around 10 points, 100%, right? And this counts 10% to the grade of this module. But in these 10 points, 1 or 2 points will be the form and professionality of the document. Because I learned over the years, over the 2 years I'm here, that the quality of the documents people upload are very different, and not all of them are on the level of a master student. And the only way how to handle it is graded, okay? So I want to have a professional document. And professional document means not completely handwritten, pages, names, okay, structure, these things. It should be readable, so just like a homework or something. So no magic, but just a normal professional document. There is no specific tasks or structure I want to see, but I think everybody you know what is meant with a professional document or not. Does anybody has questions on this? Yeah?
Like for my previous report, like there were 2 different formattings. So like, is there any particular requirement? As you specified, you don't have any type of requirement.
Mm-hmm.
Mainly in the footer, they ask for names and matriculation numbers. So any this type of requirement will be there.
So I don't have, as you said, I don't have these requirements. But if you don't have a name and don't have a matriculation number on it, it's really hard for me to know from whom it is, okay? And think about these documents are valid documents, like an exam, okay? This is an official document, like your ID or whatever. So how you deal with official documents? Okay, there should be a name on it. It should be readable. It should have a certain structure. And that's basically about it, okay? But I don't have a specific formatting, yeah? Okay. So, okay. So then this will count 10% of your homework. And I will also make a change here because the Aerosol Transport I class took 2 classes. And as I saw, it was quite good because I spent a lot of time in this part, which is important. And Aerosol Transport II, which we are doing today, is based on this. And Aerosol Transport III, which we are doing next week, is based on this. So we will have a shift in the calendar, but it will not affect the homework. Okay, probably I will skip this class because I can include this class in these two. That's not a problem. And then everything here will just go one down. So for today, what do we want to do? We want to talk about more relevant forces. And I bet I will introduce a force today none of you have ever heard. And this force is extremely important. I bet that none of you have heard about it. If one of you have heard about it, you get free chocolate from me, okay? But be honest. So far, I always won the bet. Mainly, I only make bets I win, but if you have heard about this force, let me, please tell me. And then, since the two last classes were quite theoretical, I want to talk about a lot of applications today. Because one thing, and this is also what we have here, right? Aerosol technology is a weird term, and I want to see you that there is engineering in it. There is application with the theory I teach you here. So we will talk about different applications and the relation of transports and applications. And of course, there's always the connection to nanotech. Which four terms are in the Navier-Stokes equation? So for transport, this is crucial. You already mentioned Navier-Stokes equation. Which four terms do we have in the Navier-Stokes equation? Yeah? Very, very good. So this is the equation. You don't need to learn this equation by heart, but you at least should give the answer in the oral exam, and for sure I will ask you this, exactly what you do. Transient plus convection equals diffusion minus external force. And we already played around with this equation, and this equation will today again be a little bit important. But first I would like to start with, technical applications. Whom of you know what is chemical vapor deposition? 1, 2, 3, 4, 5. What is chemical vapor deposition? You showed up, so what is chemical vapor deposition? Mm-hmm. Mm-hmm. Okay, very good. I would describe it a little bit more detailed, but it's everything correct what you're saying. Did you work with it in a lab? What did you do with it? The OLED. So it was with Thomas Justel. They used CVD in the lab. They have a CVD device. Okay. So how works the CVD? So it's maybe somebody else can explain again. So everything is correct what you say, but there are one or two things missing. You also said you know CVD, right? Mm-hmm. Okay. So basically, it's a technique to grow structures, right? So it's a synthesis technique, and of course, you can manufacture nanostructure. This is why it's interesting in this class. Do you know what was the size of the OLEDs you made? Do you remember? Yeah. And then you deposit a film, right? What was the thickness of the film? Millimeters. Okay, so you really grow a thick film on it, right? Okay, we can grow also very thin films with chemical vapor deposition, and it's a deposition method to produce high quality and high performance solid materials. It sounds a little bit like an advertisement, but basically it is. So what you need, and this is also what you mentioned, is a volatile precursor. And this is normally in a gas phase. So you have a precursor in a gas phase, and this has to be volatile, that it moves. And it decomposes or it reacts, and this happens on a surface, okay? And then you have growing of something. And of course, it's a chemical reaction. You have decomposition, you have reaction, so it means you can have byproducts. And these byproducts are produced, and then they are removed because you have a gas flow through the chamber. So you have a chamber where chemical vapor deposition happens, and everything you don't want, you want to get rid of. And there are two examples where chemical vapor deposition is used. So this one is polycrystalline silicon. And does anybody know the name of the process which is used to mainly make polycrystalline silicon? Yeah?
Siemens?
Yeah, very good. The Siemens process, developed by Siemens. And a lot of this polycrystalline silicon is done in Germany, in China, and in the US. And the Siemens process is basically a chemical vapor deposition, a specific version of chemical vapor deposition, or in this process, chemical vapor deposition is very important. So polycrystalline silicon is a very important material. And also for integrated chips, circuits here, for example, in the part where the silicon nitride, which is a kind of an insulator or a chemical barrier, this is done on the circuit by chemical vapor deposition. You also can use it to deposit metals on surfaces, or for example, like tungsten or molybdenum. They are not normally, but often by CVD grown on structures. And CVD can be distinguished by the atmosphere. What would be the best atmosphere for chemical vapor deposition? What do you think? What should be normally very good? You have a precursor and you want a reaction in a chamber. What should be normally the atmosphere there? Yeah, exactly. Vacuum, sorry. It's even worse over the microphone. Vacuum, but vacuum is expensive. So normally you do it in vacuum or in low atmosphere or even in atmosphere. Sometimes it works in atmosphere and then it's much, much cheaper. But you don't want to have any pollutants. That's the deal. And you also can have a classification of CVD process by the physical characteristics. And this means you have the precursor, and the precursor not only always goes in as a gas, it can be also goes in as a liquid. And then you kind of have to disperse the liquid into droplets, or the precursor can go as aerosol particles into the chamber. Okay, and there you already see a big connection. And for example, we will see it later. And another thing is the substrate heating. You need heat in this process, and this could come from the walls. Then the whole chamber is heated. I don't know how it was in the lab class, probably not the chamber, the substrate, yeah? So then it's not hot wall, then it's cold wall, CVD, and then the substrate is directly or indirectly heated, or you have the hot wall CVD, and then it's. And since the reaction can be quite slow, you also can have some enhancements. This could be by laser or plasma. Okay, so plasma or laser enhanced is then, so in addition in the chamber, and this is for enhancing or the grow, or for having more speed in your reactions. And another example, and this is what you see here, is chemical vapor deposition to create carbon nanotubes. Okay, so carbon nanotubes, so you have a process gas and a carbon-containing gas. The carbon-containing gas is the source you need to grow your nanotubes, and the process gas is basically to carry this carbon gas, right? So it goes into the chamber, and in the chamber you need a nuclei for your nanotubes. So here you see heating around the chamber, so you need a hot environment. And this means we have hot wall CVD here. And once the gas goes in, the reaction starts, and the nanoparticles, which as you see here, catalyst particles as iron or nickel, and then the nanotubes are growing. And basically, it could be slow. As you see, a system is the limitation of the diffusion of the carbon precursor, because the carbon precursor has to go here, and then your nanotubes are growing, 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 and the residues, they just go out, right? And here is an example of such a material, and here you see a very nice, it's called forest, a forest of nanotubes, which you can grow perfectly with CVD. Okay, so a very versatile method for carbon nanotubes, and I will give also a lecture about nanotubes, and there we will look more detailed about how people try to advance this process, and we will also calculate a little bit more there. Okay, do you have any questions to chemical vapor deposition, or is the principle of this process clear? Yeah? Okay. So another one, which is kind of an advanced version of chemical vapor deposition, is dealing with the thing that in chemical vapor deposition, the precursor goes in and you just have growing, okay? And the process conditions somehow can give you the growing conditions, but you have not very precise control about it. And when we talk about nanotechnology, basically you want to grow structures atom by atom. You want to take an atom and put it here like a Lego piece, and another atom and put it here. This is perfect nanotechnology. CVD is too rough for this, okay? I mean, you can grow nanostructures, but it's not that you take an atom and put it somewhere, okay? And therefore, we can talk about an advanced version of chemical vapor deposition. Does anybody of you know the name of this technique? Or has an idea how this is called? Physical vapor deposition is a different version of chemical vapor deposition. It's not what I meant, it's a different process, but I don't know the detail, at least I didn't prepare the details for physical vapor deposition, but you're on the right track. It's called atomic layer deposition. Okay, it's a special version of CVD, but now I have to think about physical, chemical, and ALD. And what you see here is basically how it works. So you have a surface, and the blue guys are OH groups. And you have a surface with OH groups, and then a precursor with alumina comes in. And the alumina reacts with the OH groups. But it just reacts till every OH group is occupied. So differently to the carbon nanotubes, which are growing all the time, the more precursor you put in, after a while, if we take a look now, the alumina comes in, it reacts, and then the surface is occupied. So even if I would put more alumina in, there wouldn't be any reaction. So I just grow one layer of atoms. So what I need is now a second precursor, and the second precursor activates again the first one, or the surface, okay? So alumina comes in, surface is completely occupied, I cannot grow. So what do? I put water in, and the water reacts, and I get a new layer of OH groups. So in this way, I can grow layers really atom by atom by atom, not one atom here, but at least in one dimension, we talk about atom by atom by atom. And this is a really, really cool technique. So here we have titania, and this is titania nanoparticles, and it's surrounded with an aluminum oxide layer. And this aluminum oxide layer is just a saving, okay? So, and you see that here you see the crystalline structure of the core particle, and you see the amorphous structure of the atomic layer deposition around it, okay? It's just a few layers of atoms. And here we see another one, and this is called island grow. This is for catalyst. In a catalyst, you need very high surface area. So you need small particles, and nanoparticles are small, right? 10, 20 nanometer. But these islands here are copper islands, and they are in the size of 1 nanometer. So much better, but you need a carrier for them. So you have a carrier where these islands can grow, and then you have an extremely good and cheap, because you don't need much material, catalyst. Okay, so we have these two things where you can grow a layer completely around a nanoparticle. For example, you want to save the surface. Okay, you don't want to have any surface reactions, so you just close the surface with ALD, but all the other properties are still the properties of the particle, not of the shell. Okay, for example, the color or the density or whatever. While in the island grow, you just create more and more surface area. So these two things can be done. And this means, and this is now an important point, that you can develop processes here, okay? And this is what Ruud has done in Delft. And he was thinking about, okay, how can I make really a process to make ALD on a large scale? So I take nanoparticles and I grow ALD, and I want to have a process which can do this not in a lab, but in a company. So he developed a patent. And the idea is that you have this tube reactor, And the tube reactor, you see here the blue particles are just the particles, and when they are green, they have an ALD shell around. Okay, so they go through the tube reactor, and in the tube, you add precursor 1. So this happens, precursor 1 comes in, reacts, and then precursor 1 is gone, and then later in the tube, precursor 2 comes in, as you see here, right, and this next reaction, and all this happens along the tube, as you see here. So here's precursor 1, precursor 2, precursor 1, precursor 2, and you grow, grow, grow. And once you have the reactor, you just can activate or deactivate the inlets, and you can adjust everything. But what is extremely important is if you design such a reactor is the transport of the particles through the reactor, right? So, and they figured out they need plug flow. Why you want to have plug flow in this reactor? What is plug flow? Yeah? Is the?
Increase the area, like area time. So like increase the time of the reaction to have a desired product.
Okay, how do you do this? It's correct, but how do you? You said about increase. What is plug flow again? I'm not completely satisfied with your answer. Probably it's right, but what is plug flow? Or what do you know? There's plug flow, and what else of flow? Do you know?
Plug flow, we got a back mixing, and we have conversion reaction, but more we talk about no back mixing.
Okay, no back mixing. But what is plug flow? And what kind of other flow do you know? So you have a tube, and there's a flow in it. 2 tubes. And there are 2 different kinds of flows, basically. What kind of flows do you can have in the tube? Exactly, laminar flow. How does the laminar flow looks like?
Like still, like there is no any type of motion, like wavy motion type.
Yeah, so like this, right? Right? What is the difference for plug flow? How does the plug flow looks like? Yeah? Or is it the same? Has it the same velocity profile, the plug flow? Yeah?
Plug flow is intermittent gas and liquid flow. Not a flow regime like laminar or.
But how does it look like compared to the laminar flow? Google it. Google velocity profile of plug flow.
It will be like bullet.
Like?
Bullet?
Yeah.
Like it will be the same, but somewhat tip will be outside. No? Yeah.
Yes or no?
Yeah, yeah. Right.
Yes or no? Yeah? Sure? Okay. So what is now the difference between laminar flow and plug flow? So you have to think, I inject a precursor. Right? The precursor goes in. And my particles are in the flow here, right? So what do I want to have as fast as possible happen with the precursor and the particles? What should happen? Because you want to earn money at the end, right? You want to have ALD, perfect made particles. So what should happen with the precursor and the particles? What do you want to have? Yeah? Yeah, proper deposition, perfect. And how do you get a good deposition? Yeah? Yeah, the velocity is constant. That's a very important case, but also something more happens in the plug flow compared to the laminar flow. Yeah?
In the mixing?
Yeah, the mixing.
Techniques,
Yeah,
therefore it goes faster and more evenly.
yeah, perfect. So in the laminar flow, the particles travel more or less along these lines, okay? So in the middle, they travel very fast, and on the outside, they travel very slow. And if the precursor comes in, the reaction time for particles and precursor is not equal. So at the end, you will get particles with a lot of ALD layers, and you will get particles with none or with just a few. And this you cannot really sell. So what you want to have is a particle which has certain ALD layers, and you want to have a second particle which has the same amount of, that's not a good drawing, the same amount of ALD layers. So therefore, you need a good mixing. And the mixing is much, much better here than here. So you have to adjust everything that you get plug flow. And there's another thing, when you have larger particles, around like larger than 100 nanometer, the particles have a slip. And this means they are not exactly the same speed as the gas. They are a little bit slower because they are big. And this means if not everything from the precursor perfectly reacts away, is carried away because it's faster. Okay, so you have a certain time for the reaction, everything is perfectly mixed, but for sure you will not have 100% reaction of your precursor. You will have leftover, and you like to put a little bit more because you don't want to have empty space on your particle, right? But this little bit more is carried away by the higher velocity in the plug flow because you have a slip, so the particles are a little bit slower. And this is why the transport conditions, convection, plug flow, is very, very important. And you also have to think about, when you talk about these small particles, what is the part of diffusion? Okay, because the particles will also diffuse a little bit at this size. And also you have to think about external forces like gravity and the interaction with the walls. Basically, you need Teflon walls there, which is the expensive part of the reactor. Okay, and with this, you can make a lot of products, LED, tracer particles, medical isotopes, 2D materials, catalyst, self-healing materials. This was really cool. Controlled release, quantum dots, all these things can be done. And there was a company founded called Delft IMP. It was really nice because the time when I did my postdoc, there were 2 people working at this company and they're working in the lab. And it changed a little bit because at one point when the reactor works and everything kind of seems to be a good idea, the startup grows a little bit and then you have to make one thing because you need money for your startup to get people and to make developments and all these things. And therefore, this is not so good. This is a good advertisement of your process. But at the end, if somebody gives you money, you want to have a specific application. And the specific application, do you have an idea what could be a very, I mean, this is a few years ago now, and you have this very nice ALD technology. What could be a very interesting market for advanced nanoparticles with, like I said, superior properties? What could be a really, really good market for these ones? Yeah. Yeah, 3D printings. But 3D printing is a different process, okay? So it's not a product in this case. Semiconductor could be one thing. Okay, what else? Good point.
Solar films,
Mm-hmm.
silicon layer films,
Mm-hmm.
like they want more ink
Yeah.
for that also.
Okay, this could be one. Very good. What else? Sensors. Okay, oh, very good. What else? Which market was grown in the last few years a lot?
I don't know, battery.
Battery, exactly. So then they said we go into batteries because in batteries you need powders, right? And they could show that ALD really makes these powders much, 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 much better. And then you see here, okay, they earn 10 million. And with these 10 millions, it's not so far away. The company is growing, growing, growing. And at one point, you not only change to specific one product, but you also rename your company Powall. It's for powerful powders to all. I really like this, Powall, okay? But this is then when it really goes not from research, but now we talk about startup and company is growing. But I really like the story because it was founded by these two guys, and they were just doing the research, developing these things in the lab. Okay, and this I took from the homepage. I don't know these people, but I know the people from 6 years ago, which were working in the lab. And you don't have to be a professor, but the nice thing is you can develop processes in a lab. And then you can scale up these things. And even if you don't want to make a company, you still can be the founder of the company. And you see the two right people are not on the left picture, right? But other people, if people like your process, if people like your work, then you even still can stay in science if you like it. And this is what I like the story about it. And this is a really cool thing about aerosol technology, because this is pure aerosol technology and contains a lot of the different concepts in the reactor design, ALD, and these things. And there we have a very, very practical applications. Okay, do you have any questions to this? If you want to make an internship there, just let me know. They will be probably quite happy about people. They're always looking for people. Okay, so now I would like to go again to this equation. And I told you I will introduce a force. You have never heard about it. It's an external force. I already give you this point. And the force is also important for processes, of course. And here I want to strongly relate it to a technical process. So this was a picture close to my apartment from last summer. And you saw a lot of these construction works around Münster. Do you know what they construct there or what they are doing there? Basically, when they are finished, a few weeks later, a guy rings on your bell and wants to sell you something. Yeah, so what could it be? Glass fiber, optical fiber, okay? So normally after the construction, a nice guy from telecom comes and asks you if you want to have a new contract. So what they do is optical fibers, and optical fibers are important for internet, exactly. There's the story about this new optical fiber line between Europe and US to kind of increase the exchange velocity of the, how's it called, the Börse. What's the name of, I forgot the name of Börse. Where you can buy stocks. Yeah, capital market, and then they increase the connection about a few milliseconds, and this is worth like billions of money to just have these faster connections. Okay, optical fibers. Do you think we are very good in Germany with optical fibers? What do you think? No? So we are very, very bad. Our infrastructure is quite old because we rely on electrical cables. It's not a surprise that we have Scandinavian countries and Asian countries quite on top here. But we are not really good with our optical fibers. It's from 2016, 2017 is similar. I would like to know, because they invest now a little bit. I don't know how these things changed. So, but it's quite interesting how optical fibers are produced, because we are engineers, right? So we want to think about the processes. And optical fibers are different than glass fibers. I mean, they are out of glass or out of plastic, but a glass fiber is just a fiber contained just a glass fiber, thin, long fiber. And these fibers are used normally as a thermal isolator or electric isolator. An optical fiber is different. An optical fiber has a core in it, and in this core, a light beam can travel. And based on the refractive index, you will have total reflection, and you don't lose, compared to an electric cable, you don't lose much signal over a long distance. Okay? So the difference from a glass fiber to an optical fiber is both are out of glass, but you have this core here with a change of refractive index for total refraction. And it's not so easy, because these fibers are thin, to put this one in this one. And you can think about, if you try to have a very thin fiber and you want to put another one in there, it's not so easy to do it. The thinner, the more complicated. So the best thing is you want to grow them somehow. But when you grow them, you don't start with this one. You start with this one. And it's not such a problem to make a hollow glass fiber, which is quite thick. And when you have a hollow glass fiber, which is thick, you can heat it and thin, right? You elongate it, and when you kind of stretch it, it gets thinner and thinner and thinner. You have to take care, because you already adjust a certain behavior for the refractive index. And now you have to grow something in. Oh, wait a second. You have to grow something in the fiber. And this is what you see here. So don't be confused by these many images. But what you see here is the process. And here you see the fiber. And here you just see the last image. Actually, I want to buy now such a lamp, because I think it's a nice example. But in the past, I had one. No, I don't have. And one is the inlet, and two is the, it's called the cladding material, okay? And then you have a buffer, and this is the colorful around it. So, and 1 and 2 is what I have on the board. What do you think related to this image, how this is grown? Who has an idea how it works? Take a look at the image and tell me what you see. How does it work? Yeah? Yeah, you're rotating the glass tube. The hollow tube is rotating, and what happens? Yeah, but what happens? It's okay, it's rotating, and then? Mm-hmm. 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 So we have a gaseous precursor. It's silicon tetrachloride and oxygen, and they both react to SiO2 and some other things. And SiO2 is the glass we want to have. And we had a process before. You also see it here in abbreviated. Which process do we use? CVD. So it's a CVD process, but it's called inside CVD because it happens inside. And what you create is you not directly grow this structure, you grow nanoparticles. Okay, so here in the middle, and basically I show it here on this image, because there's a very nice Wikipedia article. The Wikipedia article explained it quite well. So here the precursor comes in, you have the reaction zone, and in the reaction zone you create soot. So you create nanoparticles, SiO2 nanoparticles, they agglomerate. We will talk in a later class how this works, what is coagulation, right, agglomeration. And these agglomerates, you want them to go to the wall. So they are growing here, and you want them as fast as possible to go here and here, right? And then you just can move your structure, and then you grow the inlet. So you use a CVD process to grow nanoparticles, and they travel, so we have again transport, they travel to the walls. So how do they travel to the walls? What is the mechanism to travel to the wall? Yeah? External force, but what is a mechanism for sure we have? I talked about nanoparticles. It works quite well because we are in the middle of a tube. And what are these particles they are growing? What are they doing? No, it's not a centrifuge because they don't feel the turning. They don't feel this. So I turn the tube, but they don't feel it. Okay? It's just for equality of the heat. That's important. But what do the particles do? For sure. Think about the Navier-Stokes equation. For sure they are? Are they falling? 100 nanometer? 200 nanometer? No. So gravity seems to be not that important. Okay? What do they do? Yeah? They diffuse, right? So I just have to wait because they will diffuse, and if my tube is everywhere the same, I just have to wait because by chance they will just... So diffusion is a deposition mechanism I can use to grow my fibers. However, diffusion is for nanoparticles fast, but maybe I want to accelerate. It would be good to make it even faster. And there is a force, you said external force, you can use. Whom of you have heard about thermophoresis? So no chocolate. Thermophoresis is an external force, and here you see how it works. It's a really important one. Thermophoresis is basically Brownian motion. This is why I repeated this in the beginning. But there is an addition to Brownian motion. Look at this picture. What changes? So you see the particle and you see the molecules. And the molecules hit the particle. But there's something different to what I explained here. What is the difference? And this is thermophoresis. Yeah? Yeah, very good. So I have a temperature gradient. I have an area where it's hot, and I have an area where it's cold. And when it's hot, diffusion of molecules is kinetic energy. They diffuse more, right? So the bombardment will be different. And in a cold area, they are like slower, right? They don't want to move so much. They don't hit so much the particle. And this means we don't have equal chances anymore. In the Brownian motion, the chances are equal from each side. This is why we have random walk. But here we don't have random motions anymore. It's much, much higher, the chance to get hit from the upper side than from the lower side. So this means we will have a force acting against the temperature gradient. And this was discovered by having hot wires in a very dusty environment. So people saw that if you have hot wires in a dusty environment, you don't have any dust on them. There's like a millimeter of shield around the hot wire where the dust just don't go because of this force. Okay. And what is not so well shown in this image here is you try to, so I have the particles in the middle, and I want to have thermophoresis as an additional force to diffusion. How should the temperature gradient should be? It's not well seen here. Basically, it's a little bit misunderstandable. This is why I want to point this. So where should it be hot and where should it be cold if I want to have thermophoresis? And the particles are growing in the middle. Yeah? Yeah. Very, very good. So it should be gradually colder and the walls should be cold. Because if the walls are cold, it's like a magnet for the particles. Okay? So you have diffusion and on top you have thermophoresis, and this accelerates. It's very simple. Okay? You just need a little bit heat and you significantly increase your growing. It's an extremely simple and cheap mechanism. So thermophoresis is calculated quite easy. So this is the equation for free molecular regime. What is free molecular regime? Yeah? In this area are no molecules. What is free molecular regime? What is the regime you mean? What is you mean a different regime? And you said there are no molecules. What regime is this? No, not, I'm not talking about atmosphere. I'm talking about the regimes. We had this on the slides before. Which kind of regimes do you remember? We repeated this last week also. Yeah? continuum and transient and free molecular. Very good. And free molecular means, or continuum means, you can do it vice versa. What is the meaning? Your statement was correct, but for which regime? You said the particles, there are no molecules, they don't exist. So which regime is it? Yeah? Okay, you don't know? Which regime? Which regime? Yeah? Yeah. Yeah, very good. And what does it mean to his statement? It's correct what you're saying. It's not 1 nanometer, it depends on Knudsen number, right? But what does it mean? Because he said in free molecular regime, no molecules exist. Where do no molecules exist? In which regime? Any idea? Okay. Continuum. Okay. The assumption of continuum is no molecules. The continuum has a density, has a temperature, has a density gradient, whatever. But you don't consider the molecules. The transient means you use continuum equations, but you already have to make some adaptations because you see effects of molecules. And free molecular regime means you take into account each single molecule and you have to calculate everything by statistics, okay? The movement of each molecule. And if you take a picture, a look at this picture, this is free molecular, right? We have a molecule here, we have one here, we have one here, and this would be continuum, okay? Hot gradient, cold gradient. There are no molecules in this. Okay, so this is a very nice difference for continuum to free molecular. And the equation for free molecular regime for the force of thermophoresis is a quite simple one. So this is the force, and there's a pressure, and there is this lambda. We already had lambda last week. Who remember what was lambda? What was lambda? Do you remember, Yajiro, do you remember the lambda? Okay, that's fine. Last week we had it related to the Knudsen number. What was the Knudsen number? Yeah, mean free path, okay? So this is the distance a molecule travels before it hits another molecule. Here it would be 66 nanometer. And Knudsen number is 2 times mean free path divided by the size of the particle. And if the Knudsen number is larger than 1, we have free molecular regime. And if it's smaller, continuum. Okay? These are these relations. So we have the mean free path, we have the particle size, the temperature gradient, and the temperature. Very simple to calculate. Okay? In atmosphere, you have half of these numbers. The only thing you don't know is the temperature gradient and the size, but it's very, very easy to calculate. And from there, you can also develop the velocity, because thermophoretic velocities, right? Think about your reactor where you want to make glass fibers. You want to know the velocity of the particles going to the wall. And this is an extremely simple equation. So you have 0.55, you have the viscosity, the temperature gradient, the temperature, and the gas density. It's extremely simple to calculate how fast your particles are in your reactor. It's even independent of the particle size, interestingly. It only counts for particles around 100 or below 100 nanometer, but then it's not anymore influenced by the particle size. For continuum, it's not that simple. For continuum, the force and the velocity is a little bit more complicated, and this is due to this term here, h. And the term h means that if you have a large particle, okay, this should be a large particle compared to the small particle, and we talk about temperature gradients, okay? I just have to, okay, it's working. Temperature gradients. So you have a temperature gradient in the surrounding, but for a large particle, if you have a very hot upper gas and a very cold lower gas, what happens to a large particle? Yeah? It goes for equilibrium, no. The particle is affected by the surrounding, but not for equilibrium, in another way. It is correct that it's affected, but not for equilibrium. So you think you have a very, yeah? Yeah, a large one will settle due to gravity, but we neglect this. Just think about me, and here it's very, very cold, and here it's very, very hot. What would happen to me? And I don't have circulation, or I have circulation. We can keep this there. What probably would I feel? Yeah, where do I feel cold? Here or here? Where it's cold, right? So it will even affect me. Probably my feet will be cold and my head will be warm. So a big particle has inside also a delta T. For the small particles, we can neglect it. But for large particles, we have to consider that there is the temperature gradient from the outside will be seen in the particle. And this is what you have in this term H here, okay? And Kg and Kp is the thermal conductivity, okay? Third semester heat transfer. And this is just what happens in the particle, and this affects the outside again. So this is why continuum is a little bit more complicated. But at the end, you can calculate it quite simple. Mean free path, size, and these numbers you can look up on Wikipedia. Thermal conductivity of materials you will find on Wikipedia, very simple. So both are easily to calculate. And here I would like to show you the influence of thermophoresis. So what you see here is the terminal and the thermophoretic settling velocity. So terminal settling velocity is what we calculated for the sand or for the droplets. And you know how to calculate it. And if you want to repeat a little bit this class and try to understand what we do, make the calculations, okay? Assume a particle, whatever you want. The sizes are here, and most of the things is standard conditions. So you should know the density of air. You can assume a certain the temperature gradient is given here, okay? So the temperature and the gradient is given here. So make the calculations. Look which force balance they use. Do they use buoyancy or not? And try to see if you are in the same size ranges. If you don't have 2.8, if you have 4 point something, probably you choose a different material or whatever. As long as you get 10 to the power minus 6 for the 10 nanometer, everything should be fine. It's a very good exercise. You already have the solutions. And here you see that the thermophoretic velocity is quite comparable in these regimes here, okay, to settling. The settling here doesn't happen, so here the thermophoretic is much, much higher. And this is what we know. Settling is important for large particles, but the smaller the particles, we cannot rely on settling. So we have thermophoretic, and the other one is, as you mentioned, diffusion. And here you see diffusion compared to thermophoretic. And this is not in terms of velocity, but this is in terms of particles deposited per square meter. Okay, so think about the tube. You want a deposition of in the inside. And here you have just pure diffusion and pure thermophoretic. And you see that especially in this size ranges here, the thermophoretic really significantly improved the process, okay? And your particles you get are not all 10 nanometers, so you cannot rely on this high diffusion rate. You're somewhere here, and then thermophoretic is really a plus. Any questions to this? So I would like that you understand the mechanism, and you should have an idea what is in the equations. I will not ask you equation number by number, but you should know what is in these equations, what is important, what is the driving force. What is the relation of thermophoresis to Brownian motions? How does thermophoresis work? Do you know examples for thermophoresis in industry? And the last 15 minutes, I would like go on with examples. And this is a technique I really like to create nanoparticles, and this is flame spray pyrolysis. We will see this more and more and more. And this is here for gas sensors. And in the flame spray, here you have the precursor, it's a liquid, and you disperse it, and the droplets are burned. And then you have nucleation, aggregation, agglomeration, and you get very nice nanoparticles. And the problem is that it looks quite simple here. Here is the substrate where you want to have your gas sensor. And the flame goes like this, so the flow goes like this, and the nanoparticles also go like this. However, for a real flame process, you have a little bit of problem, and sometimes the materials you spray are very expensive, so you don't want to lose them. So it means you have your flame, and you have your gas sensor, and not all of the particles directly go like this. So what happens is this one. So and the particles go here and here. So you have a lot of losing material. Take a look at the picture, what they are doing to avoid this. Again, that's something I really want to teach you in this class. Applying the principles you learned from the theory. So you know thermophoresis, you know we have a problem that we lose a lot of particles, and you can apply a principle to solve this problem. Very, very simple, in an extremely simple way. Yeah?
There's a support flame on both of
The support flame you need, it's a methane flame. The support flame is like around here, and you need it to stabilize the big flame. Even much, much simpler. Think about thermophoresis.
I think we can have a buffer atmosphere around that, maybe colder, that it goes straight to the sensor.
Yeah, you're on the right track, but even simpler and more specific. Where will it depose? On the hotter or on the colder? On the colder. So what should I do with my sensor? Yeah, because the particles out of the flame are already hot. Okay, they come out of a flame. They are hot. So what I just need to do is cold water. And what do my particles? Zack, zack. It's like a magnet. You know the science of magnets. And in this way, you improve the amount of particles you collect. So applying a very simple principle to improve the process. Okay, so thermophoresis can be used here to collect. Here you see cooling water goes in, deposition substrate, and thermophoresis is a nice gimmick you get to increase your, you will not collect all of them, but you will have an effect. Okay, another example. Who knows this law, Moore's law? What is the meaning of this law? Or what is this law? It's a diagram. Yeah?
Moore's law, I think, is about the CPUs or electronic chips that the number of transistors can increase exponentially. I think up to a higher
is everything correct what you're saying? But there was even a fixed number how it grows. So the amount of transistors on a CPU or on a circuit increases. How? It doubles every 18 months. That's Moore's law, or 16, but I think it's 18 months. And Moore is a guy who just looked at it, at the amount of circuits on a transistor, and then he figured out it doubles every 18 months. So he just made the points in a log over time diagram, and this means the circuits get smaller and smaller and smaller, the transistors get smaller and smaller, so you have more space to put it, nanotech, right? Smaller, smaller, smaller. And this works so well that it was taken as a guideline for the industry. So it means that the industry tries to obey Moore's law, and they say, okay, in 18 months, our product has to be there. Sometimes it was really hard for them to reach it. Sometimes they even overpower the law. And then they say, no, no, the market is expecting this, so we can slow down, we can earn money, even if we are better. This is what the market accepting, and we go with it. So it has advantage and disadvantage. It's not proved, it's just empirical, okay? But sometimes these empirical laws are so powerful that the companies work on it. And then there was always the question, when will Moore's law end? And then they always say in 10 years it will end, in 10 years it will end, in 10 years it will end. And one very big question was, I mean, think about free molecular regime, right? So a circuit is like a copper line, but if you go smaller and smaller, so if this is 10 micron in diameter, it's a line, continuum. But if we go to 1 or 2 nanometer, how would this line look like? What do I have to change in my image? 1 nanometer, or half nanometer, or 2 or 5 nanometer, I don't know. Could I still say it looks like this? What do you think? Okay, so this is 10 micrometer of copper. Right? And I can just say, okay, it's 10 diameter. So now I would say 1 nanometer. Would this, for 10 micrometer, it's a very good model of my line. Is this a very good model for such a small structure? Think about this image here. What's the difference from here to here? Out of what does the copper consist? Atoms, exactly. And at one size, I should see them. I cannot just say that if I go very small, it should be more like this. And then if I decrease the size, I also have certain quantum effects and so on. So there is a limit. The question is always, where is the limit? And yet we didn't found the limit because now we are at 4 nanometer and the transistors still obey Moore's law. Okay? You already saw the next slide. Whom of you know ASML? It's a company. It's one of the most important companies we have in Europe. Who has never heard about ASML? All of you, right? What do you think? Which country is it from? Yeah? Yeah. Do you know? You should probably know what they are doing. You know. So, what is ASML doing? There's a reason why you should know what they are doing. Yeah, exactly. Which country, and this is what you should also know, is producing the most semiconductor, the circuits and all these things? Huh? Taiwan, right? 80%. So, but Taiwan is producing them, but not producing the machines the machines are produced by a Dutch company. And this company is called ASML. And it's a very, very tricky technique to make these machines. And the technicians in Taiwan, maybe you know it better than me, but if they get a new machine, they are trained about 18 months on the new machine. So it's really complicated. And so ASML is producing photolithography machines. And what we have is patterns are optically imaged onto a silicon wafer that is covered with a film of light-sensitive material. And the photoresist is further processed to create the electric circuit, okay? So this happens in Taiwan, but the machine is developed by ASML. No, I don't think so. I don't know about... I think it's a nice homework for you to figure out. As far as I know, not, but I don't know the history of ASML. Yeah, but he will say for sure. He will always provide Philips. So, but I don't know. So figure out if ASML is a residue of Philips or not. But it's extremely a successful company. I don't know why you should give it away. They have 12,000 patents, and they are basic, as far as I know, the only company who can build these machines. And this is really, in Europe for us, a really important company. Okay, how does this photolithography works? How do we get these circuits to life? And the process is quite well understood or quite well known. Is you have a wafer, okay, the substrate and an oxide. And first of all, you have to clean the wafer. You don't want, that's something you don't want. You don't want to have any pollutions on your circuit. It's so small, if you have pollutions there, it doesn't work anymore. What could be a source for pollutions for circuit wafer? Extremely important in this technology. What could be a very important or dangerous source for pollution when you want to create or synthesize or produce a circuit? How many particles are at this moment in this class? Yeah, but we learned a number, very specific number. 10,000 per cubic centimeter. So now you want to make a circuit, 1 centimeter, and you have 10,000 particles. Is this good or can you ignore it? Right. So what is a very big source for pollution? What is a big problem in producing circuits? Again, sorry, I didn't.
Aerosol in the atmosphere.
Yeah, exactly. The aerosol part, the dust. The dust is a really extreme big problem. So the knowledge about aerosol technology is extremely important in this part of production. So once it's cleaned, and this happens in clean rooms, because clean room is doing what? The clean room reduces the number of particles, but they are still particles, and they are still like killing your circuits. So you apply a photoresist, and basically you also have an adhesive that the photoresist glues better to the oxide. And once you have the photoresist, and now the important part comes, you have a mask. And the mask is basically how your circuit looks like. Okay, this mask is the really expensive part because you have a silicon wafer and through the mask you can make thousands of these circuits, but the mask is the really expensive thing. And then the mask is above your wafer and then you expose UV light. And the UV light reacts with your photoresist. And just where you have a reaction with the photoresist, it chemically changes, and it can change in two ways. It can make it it can make it unsensitive to further chemicals or very sensitive to further chemicals. And normally the reaction goes that this area is now very sensitive to other chemicals. So it means everywhere where the photoresist is exposed to the UV light, the photoresist is sensitive. And where it's not exposed to the UV light, it's not sensitive. And this means that this picture, what you see here, or you kind of have a structure, and the size of the structure depends on the wavelength of the light. This is why we use UV light, right? UV light has a very small wavelength, and with a small wavelength, you can make these structures which are exposed very small. And this makes these machines so expensive because you want to have, with ongoing Moore's law, smaller and smaller transistors. You need smaller and smaller wavelengths, okay? With a wavelength of 400 nanometer, you cannot make a 4 nanometer structure. You only can make a 400 nanometer structure. Okay? So that's a little bit oversimplification, but that's the limitation you have. And now, when you have these areas which were exposed, the mask goes away, and then you can put a chemical into it, and the chemical will react with the photoresist, and then you see you can get rid of the photoresist, and now you have areas where the oxide is there, and where and now it's like a free area. And what you do is then you etch, and the photoresist, which is still there, protects your substrate below from the etching. And where the photoresist is gone, you can etch away the structure. And you cannot use liquid etching. What is the problem if you use liquid etching? So if I etch and I put a liquid in here, what would happen? What happens if a liquid goes in here or here? What happens with my oxide if I put a liquid in here? It would react, but how? So what if you look at the picture E to F, and this is exactly what I want to have. Would I get it if I put a liquid? So I have my photoresist, and then I put here a very reactive liquid, which kind of etches away the solid here. Would I get the picture of F? It will react also here and here, right? It will just go everywhere. So what you use is ion bombardements, ion etching. Ion etching is just straight, so you don't have reactions to the side. And then you can quite simply afterwards remove the photoresist, and this is how we generally make integrated circuits, yeah? Uh-huh. Mm-hmm. Which one? Yeah, but you have to, I mean, you can use it, but you have to be very, very careful about how this goes here, right? So normally, or as far as I know, mainly they use ion bombardements, not always, but you can use the liquids, but you always have the disadvantage that the liquid can or you have no blocker here to the right and left, okay? But actually, it would be nice to figure out, maybe it's a nice homework for you, what is the main etching process, and if I'm right with the statement, or if liquid etching. I will ask you next week, okay? It's a nice homework. It's not much research. I think you figure it out very, very fast, okay? But now I'm interested. Okay, so here's just the picture. I will not talk too much, but you have the mask, and you do this step by step by step by step, and this is how it happens on the silicon wafers. So now the problem is you don't want to have particles on the wafer. They kill your circuit. And even in a clean room, you still have a few particles. So now think about a concept how you can save your silicon wafer for sure from particles. What can you do in your process? Very simple. You vacuum it, but even there you still will have some residual, and it's very expensive to have very, very high vacuum, and you have to close everything, and then wet etching, so liquid goes in. What else? Much cheaper, much simpler. So how? Yeah, cold or hot, that's good. Cold or hot? Think about the principle. I don't want that particles go in this direction. I want them to push in this direction. So what could I do? Yeah?
Like the surface should be hotter than the...
So this should be hot. And it's the completely opposite from here. And if I do it, I will have a shield which saves my circuits. And this is what you see here. Okay? So here is a delta T of 0, and this is a wafer under clean room conditions. And you see that you still have a lot of particles. Each dot is a particle. And if you just apply a temperature difference of 10 degrees, this happens. Okay. Extremely powerful to save your circuits. And then there is a nice experiment where they have here the shower heads, like in a shower, and then the particles come out, and they have the divider, so you have a left and a right part, and you can switch on warm or cool. So you have cool, and then it's protection, and warm, protection is off. So cool means, so warm means protection off. So it means you also make it hot here, and cool means you cool it down here, so you have the temperature gradient. And then you can see how you can even play around with it, okay? So depending on one is off and on, here you get no thermophoresis, so the particles go on your wafer. And here you have thermophoresis, none of them goes there. So it's a really, really nice, I really like this example because it's a direct application of a theoretical force, of a theoretical concept used in a lot of industries. Good, with this we are finished with the class. So I hope you learned another force. I hope you can explain this force now, and I hope you learned a little bit about different applications which are related to aerosol technology. We talked a lot about processes and the relation of transport to application, right, in the semiconductor industry, and also a little bit about nanotech. And with this, we are finished for the class, and I will upload till tomorrow your homeworks.